Hello everybody, in this lecture we will be solving 1986 IMO problem number 4. Here's a view of this problem. We're given a regular n-gon with center, I assume, at point O. So let me first locate that center here. And then we have a bunch of isosceles triangles, I assume, which are kind of connected, obviously, like this. That kind of makes sense, what's going on, huh? And you have some more, obviously. Oops. So probably like that. I should change my picture. There you go. Okay, so we have the center point O, and we have a bunch of A, B, C, and so on. So all these other things. And what happens is we have another triangle XYZ, which I will probably draw with another color, say it red, which traces out, which is congruent to AOB, and it traces out the boundary of our polygon, right? So what I will do is, so this XYZ, so would look like probably something like, oops, like that, as it traces out. So that's point Y, that's Z, and that one is X. So as it traces out on the boundary of our n-gon, the question is asking for the locus of the points X. Obviously, each 360 divided by n degree rotation, we will end up where, if for example Y started at point A and Z started out at point B, then Y and Z will move and then they will reach point B and C respectively, and so on. So you can imagine that X will start at that vertex O, and then it will somehow go away from O, and then it will come back periodically, n times. So every 360 divided by n degrees, X will be back at the point O. Okay, so far let's write down the given. So we are told that AOB is similar to triangle, obviously YXZ. So in order to accomplish finding the locus of the points, I would like to start by chasing some angles. Okay, so my claim is that I claim that B is on the circumcircle of XYZ, basically. So that's kind of the critical observation, which is actually not very hard to prove at all. All we need to check is that those two angles, so basically prove that angle YXZ plus angle YBZ, right? Oops, sorry for that. Angle YBZ add up to 180 degrees. Now let's be careful on that. So obviously YXZ is equal to AOB because of this similarity, right? So therefore I will replace YXZ, the first angle here, with AOB, right, plus excuse me, for the second angle YBZ, obviously you can split it up into two pieces here, which is ABO plus OBC, angle ABO plus angle OBC. But check this out, angle OBC is the same as angle OAB. So therefore this whole thing becomes angle AOB plus angle ABO plus angle, replace OBC with OAB, and we have the three angles of triangle AOB. As a result, they add up to 180 degrees. So we have just proved that those 4 points are cyclic actually. So therefore YXZB is cyclic. I claim, again, a second claim, let me write the claim, another very simple claim, that BOX, BO and X are collinear. And again, the proof is not too hard actually. Let's start with angle OBZ. So obviously angle OBZ is equal to angle obviously OBC, but we know angle OBC is equal to XYZ, right? Angle XYZ, and angle XYZ is the same thing as, well, because we have this cyclic quadrilateral, on the cyclic quadrilateral, XYZ is the same thing as XBZ, angle XBZ. So we have just showed that OBZ and XBZ are the same angle, suggesting that, because BZ, that line segment, is the same, so giving us the desired result, right? So showing that B, O, and X are actually collinear points. So therefore, we have simply proved that the locus of X would look like, so rather than looking like a flower petals like this, that's not the way it will look like. It will rather look like this. So you will start at point O, we will go back and front, and then every 360 over n degrees we will keep doing the same thing, going back and forth, back and forth, back and forth, back and forth, and so on. So that's what this shape looks like. So it looks like an asterisk composed of n line segments. The remaining part, and this is a line segment as well, sorry for the bad picture. So, and next the goal is to find the length of this one of these little lines, so to find the length of any given one of them, because we have a symmetric shape. So we call this D, and in the next part I would like to show this length. So what I will do is I will just move things a little bit, so oh, sorry for that. Yeah, so therefore now one crucial observation will be that, let me go back to the blue color again, the idea that it will be that length, the maximum length will be reached for the length D will be reached when Y and Z are symmetric with respect to OB, right, in our previous picture. So let me draw AOB in a special way, like that, I assume, like this. So that's my AOB. O is somewhere here. And then I'll draw the next guy as well, so which is actually, let's just revise it a little bit. Oops, sorry for the drawing. Okay, so, and let me make a quick revision here. Okay, looks good. Okay, so I'll just, oh, sorry for that. I'll just redraw it carefully. Okay, good. So that's the point C. And so my earlier claim was that the picture should look like this. Oops, sorry for that. So the picture will look like something like this. Symmetric. Oh, symmetric with respect to this line OC. So actually, let me get rid of this. So we have, so this point here is X, and O is over here. So right. So that's where O is, and the distance here, now we can make sense of that distance. So in fact, let me go ahead and make a couple of observations. So first of all, the circumcircle of the n-gon, let's say that it has the circumradius of n-gon, let's call it as capital R. And for the circumcircle of XYZ, or the circumradius of any given little triangle, but in particular what I have in mind is XYZ. So circumradius of triangle XYZ, let's call it as little r. Obviously, so as I said earlier at the beginning, right, so the shape is symmetric, so suggesting that this is equal to this. Be careful, Y and Z are not the midpoints of AB and BC respectively. They are not. So that would give you the wrong idea. But because XB is the diameter of a circle with diameter 2 little r, the question, the D, which is the distance between O and X in this particular moment where the Y and Z are symmetric with respect to OB, so that little distance here, little d, will actually be equal to 2r, obviously, right? So 2r is the diameter of xyz. So let me go ahead and draw this, if you will, right? So xyz, something like this. So the diameter of this circle is 2r minus the radius of our guy, Rn gone, so which is this guy, which is r. So that's what the question is asking from us. I suggest that we can apply the extended law of sine on triangle, extended law of sine on triangle OAB. Notice that OB is equal to R, right? So OB here is equal to R, that red line. As a result, the angle, we will make use of this angle here. So therefore, I would say that R over sine of angle OAB is equal to 2 times the circumradius. Obviously, the circumradius of triangle OAB is the same as the circumradius of triangle XYZ, because these are congruent triangles. So 2 little r. And now notice that when we do some angle chasing, angle OAB, let's do the, I guess the angle chasing here, over here. Let me open some little box. So angle OAB is simply equal to 180 degrees minus the central angle AOB, which is 360 over n over 2. So what we get is 90 degrees minus 180 over n. But the sine of this angle would be the cosine, right? So we can replace the sine with the cosine, 180 over n. So therefore, so you can say that 2r is equal to r over cosine of 180 over n. And now it's time to plug it into the original expression, and factoring out the r, we get that 1 over cosine of 180 degrees over n minus 1 is the size of those branches of asterisk. So again, the locus as a result turns out to be the point O here at the center. You go and come back, go and come back, and so on. So you have this nice shape where each of these lengths of each of these branches turn out to be equal to this distance here, and we're done.